This talk is about how we exploit bounded staleness to speed up big data analytics. And getting useful information from data is becoming more and more important, and quite a lot of work from both the system side and also machine learning side that try to accomplish this work more efficiently. And here I will first describe the specific class of big data problem that we are targeting at. Suppose we have some huge input data, which can be a set of documents or web pages, and we design a model that tries to explain this input data. For example, these models can be the clustering of documents with similar topics, and we build a program to solve the model parameters from the input data. And the algorithm is usually iterative, that it first makes an initial guess to the model parameters, and then it goes through each entry of this input and make adjustment to the model parameters. And because the adjustments coming from one input entry can change the decision of another one, so we need to go through the input data multiple times until the model parameters converge, and we call one pass over this input data as one iteration. And to make this program parallel, we can divide the input data into multiple partitions and have each thread to compute only on one partition of the input. So these threads will concurrently update the model parameters based on its local input. And to make it easy for application developers, people are building systems called parameter servers to manage the global shared model parameters. And in order to make the parameters converge, this communication thread, the parameter server actually provides mechanisms for this communication thread to synchronize their updates. And a common approach to use the bulk synchronous parallel. But in a large system, this approach has quite a lot of overhead. And our work is to explore different synchronization models for parameter server that try to reduce the synchronization overhead while still preserving reasonable consistency. In this talk, I will first discuss two novel synchronization models as extensions to the bulk synchronous model. Then I will introduce our prototype system that supports both models. And finally, I will show some selected experiment results. Traditionally, machine learning applications are often paralleled using the bulk synchronous parallel or BSP model. In BSP, the execution is divided into clocks, and each clock has a barrier at the end. And when the computation thread finishes the work of one clock, they propagate their updates and wait for the other threads at the barrier. So in this figure, these bars represent the progress of each thread. And now this thread 1 is blocked by the barrier and waiting for the other two threads. The clock is usually defined every fixed amount of work. And the common use of BSP is to use one iteration over the input data as one clock. And BSP guarantees that the threads can see all the updates before the previous barrier. And in this figure, thread 1, for example, cannot see the updates of clock 2 from the other two threads. As a result, BSP implies that the threads can see out-of-date values for the shared parameters. And we call that data staleness. And machine learning applications can usually tolerate this data staleness. And moreover, sometimes we even want to allow more data staleness because it can increase the system performance, because the computation threads can synchronize less often and they can use more stale data from their local cache instead of fetching for the latest one. And certainly, too much staleness can hurt the convergence, making the program converge very slowly or even diverge. So it's important to make data staleness bounded. And we point out in this paper that data staleness should be a first-class tunable parameter. And we discovered a more general use of the BSP model that allows us to explicitly control data staleness. We find the work in each clock does not need to be exactly one iteration. Instead, it can be arbitrarily chosen, and usually we use a multiple or fraction of one iteration in each clock, and we call that iters per clock. In this example, we do 2 iterations in each clock. By changing the iters per clock, we can explicitly trade data freshness for speed, and the larger iters per clock make the program run faster by reducing the synchronization frequency, but at the cost of allowing more data staleness. So even though it's still BSP, we call it arbitrary size BSP or ABSP in this work in order to distinguish this more general use from the common practice. Even though we can reduce synchronization overhead by having a larger work per clock in ABSP, we still have the problem of stragglers, because all threads have to wait at the barrier, so a slow thread will slow down the whole system. And there are many reasons for stragglers. Example includes the loss of network package and software activities such as garbage collection. To solve the straggler problem, we proposed another model called Stale Synchronous Parallel, or SSP. In SSP, the execution is still divided into clocks, and the thread propagate their updates at the end of each clock. But instead of having barriers, SSP allows each thread to be some number of clocks ahead of the slowest one, which is controlled by a slack parameter. So in SSP, different threads can be working on different clocks at the same time, as long as the fastest thread is no more than slack clock ahead of the slowest one. So here is an example of SSP with a slack of 1 clock. You can see that thread 1 is at clock 3, while thread 2 is still at clock 2. And so a larger slack means less synchronization. As a result, changing the slack parameter is another way of controlling data staleness. SSP also allows arbitrary amount of work in each clock. So ABSP is actually a special case of SSP where the slack is always 0. And the two parameters of SSP form a two-dimensional configuration space. And there are actually multiple ways to achieve the same data staleness bound. And as we discussed in the paper, that any SSP configuration have a counterpart of an ABSP one that provides the same data staleness bound. And in the rest of the talk, I will focus on comparing two approaches. The first one is to do exactly one iteration in each clock, and have the slack using SSP, and the other one is to use ABSP that do multiple iterations in each clock with no slack. Next, I will briefly introduce our prototype system called LazyTable. LazyTable is a parameter server that manages the global shared model parameters for big data applications. It supports the SSP model and also the ABSP model using a slack of 0. LazyTable is composed of a cluster of tablet servers and a client library. The parameter data managed by LazyTable is sharded among multiple tablet servers, and the application workers access this data through the client library. The tablet server and the client library, the application clients can run in the same set of machines. And our system also has multiple levels of caches and use prefetching to reduce latency. And please read our paper for more implementation details. Next, I will show some selected experiment results from our paper. For most experiments, we use a cluster of 8 machines. Each machine has 64 cores. And on each machine, we launch one client process and one tablet server process. And the client process creates 64 threads, 1 thread per core. We run experiments on several real-world machine learning applications. In this talk, I will focus only on topic modeling application, and for other applications, we discover similar behaviors. And we use a New York Times dataset for this application. And this dataset has 100 million words in total. We use log likelihood as the solution quality matrix, which essentially means how likely the output model can generate the observed data, so a larger value means a better model. In the first set of experiment, we show the trade-off of data freshness and the system performance under both SSP and ABSP. We first run SSP with iters per clock being 1 and change the slack parameter. The first graph shows the iteration speed. Here the x-axis is time and the y-axis is the number of iterations completed. When the slack is 0, it becomes the traditional BSP case, and we use that configuration as the baseline. And when we increase the slack to 1 clock, as shown in the blue curve, it completes more iterations in each second. That's because the computation threads are less likely to wait because of the reduced synchronization. And we continue to increase the slack. The iteration speed continues to increase, but the returns are diminishing. And generally, as we increase the slack parameter, the program can complete more iterations per second. The second graph shows the convergence quality after completing some number of iterations. So here, the x-axis is the number of iterations completed, and the y-axis is convergence. The exact value of this y-axis doesn't matter because we are only compare the cost of reaching the same convergence using different configurations. The black curve shows the convergence of the BSP baseline after doing some number of iterations. The blue curve shows the result of a slack of 1 clock. The right way to understand this graph is to draw a horizontal line and compare the number of iterations it needs to reach the same convergence. So here, with a slack of 1, we need more iterations to reach the same convergence because the threads use potentially more stale data for their computation, and that hurts the convergence, hurts the quality of each iteration. Generally, as we increase the slack parameter, the effectiveness of each iteration decreases, and the program needs more iterations to reach the same convergence. So there's a trade-off between the speed and the effectiveness of each iteration. And combine these two factors, we show a graph of convergence over time. So here, x-axis is time used, and the y-axis is the convergence. We draw a horizontal line again and compare the time it takes to reach the same convergence. The results show that with a reasonable slack, SSP can reach the same convergence in less time than BSP. For ABSP, it behaves the same way when we increase iters per clock, and a similar effect also have been observed in other applications. The takeaway message is both SSP and the ABSP are ways of explicitly trade data freshness for speed, and with more data staleness, the iterations goes faster, and we need more iterations to reach the same convergence. And combine these two factors, there's a sweet spot in the middle, which can only be achieved when data staleness is tunable. In our basic experiment settlement, we find that the performance of SSP and ABSP are similar. That's because our carefully controlled experiment test bed minimized the variation of the thread speed, so there are no stragglers in the system. And what if we have stragglers? To compare the behavior of SSP and ABSP in face of stragglers, we designed some experiment that artificially introduced stragglers to the system. Here we'll only show one of this experiment. We emulate stragglers by introducing some background CPU-intensive work to the system, which is a very common source of stragglers in a shared cluster. We designed the following experiment. We'll create one disruptor process on each machine and have it take half of the CPU when active, and we make the disruptor randomly work or sleep. The duration of each disrupt is t seconds. We pick one SSP configuration and one ABSP configuration that provide the same data staleness bound and compare their behaviors in face of stragglers. So here the x-axis t, which is the duration of each disrupt, and the y-axis is the percentage of runtime increment due to the disrupt. Ideally, the disrupt only slows down the execution by 5%, because on each machine, the disruptor is active for 10% of the time and takes half of the CPU. The blue curve shows the result of ABSP. Essentially, the execution is slowed down more when the disrupt is longer. The red curve shows the result of SSP. It provides the same data staleness bound as the ABSP one. And the duration of each disrupt, when the disrupt is smaller, it's transient straggler and can be mitigated by the slack. And in that case, the behavior is close to the ideal curve. And when disrupt is longer, the stragglers become constant stragglers, and we should use load balancing techniques. So compared to ABSP, SSP is more tolerant to transient stragglers. To conclude, in this work, we formulate the concept of data staleness. We show that it can be tuned by changing iterations per clock and/or the slack. We describe the imputation of lazy table. We suppose both SSP and ABSP. And we do extensive experiments showing interesting results. First, ABSP and SSP are ways of exploiting the staleness sweet spot for faster convergence. And second, SSP is more tolerant of transient stragglers. And third, SSP incurs more communication traffic due to its finer grained division of the clocks. And I did not cover that part in this talk, and please read our paper for more details. Thanks.
Xiao Zhang from Google. Very nice talk. I'm wondering, looks like the sweet spot in your configuration heavily depends on how badly the straggler operates. For example, if it slows really badly, your sweet spot may shift differently. Did you consider optimizations such that it can boost the slowest straggler performance to have sort of a bounded straggler, such that the sweet spot for the system is always more consistent across different straggler performance?
So are you saying that we should try to make the stragglers, try to help the stragglers catch up with the faster threads?
Yes.
Yes, actually our assumption that the threads have averagely the same speed, so we assume that once a thread becomes straggler, and as long as it's not too slow, it can be tolerated, and as the threads execute, the faster thread will later become stragglers also, and in that case, when their average speed are similar, they can catch up. And actually, because we have multiple levels of caches, the slow thread actually have less overhead in their execution because they don't need to fetch for the data again, for example. And so these are mechanisms to help the stragglers catch up. And did that answer your question?
Sort of. Okay, thank you.
Okay.
Yeah, Chuck from NEC Labs, Princeton. Now, in your experiments, did you compare the quality of the result? In other words, you have two methods, SSP, ABSP,
Yeah.
and I'll run the iterative algorithm through that. In our experience, the final result you get by using staleness is a little different than the final result you get using a regular BSP. So I didn't see any comparison of, is the final result the same in your two schemes?
Final result, do you mean the model?
The model.
The model.
The model has to be evaluated to make sure, because the two methods will produce two different models. And I think the real test is to make sure that these things are effective wherever they are used. And we observed that when you actually put it in an environment where we use the models, the quality of the models is so different.
Actually, we use this log likelihood as the matrix for the model quality. And our assumption is actually when the log likelihood is the same, we assume the models are the same. Actually, it's not necessarily true.
It's not true.
Yeah.
So that's the concern.
But anyway, a larger log likelihood will imply a better model. So we use that as the model quality matrix. And yeah.
Right. What we observed is if you have zero staleness,
Yeah.
the model has a certain accuracy and it is considered good. But when I start deviating from zero staleness and start putting a little more staleness, what we noticed is the relationship between staleness and accuracy first is nonlinear. Second, the relationship is not even monotonic. It doesn't mean that more staleness really hurts or less staleness improves. It's not even So once you get past zero staleness, then it's a very slippery slope out there. There's absolutely no relationship between amount of staleness and the actual quality of the result. So I can see you can control the speed, that's good, but we observed that that's what's happening. How are we measuring quality? So what we did was we took the models and put them in an environment where you're testing it. Let me give an example of cancer diagnosis. So we looked at histological samples of millions of cancer slides, and then from that we built the models for detecting, okay, these are possibly cancerous cells. So now we got the model. Now this model is actually used in environment where we are seeing how we are classifying the slides to be cancerous or not and what the doctors are doing out there. So we have a way to compare how good our model is and all that. Then we went back to creating the models using different approaches where we put the staleness in play. Then we observed that the models we are getting is having this behavior where what the doctors are rating and what these two models are doing is quite different. Well, I don't know what log likelihood is doing, but in the real situation that we looked at, it is a real issue that when you start playing with staleness, you get different answers, and these different answers affect the final environment very differently.
Actually, what I want to point out that even using BSP, there's also data stillness. So the model we get is actually not exactly the ground truth model, and we are not introducing data stillness. We are just tuning this data stillness and to achieve various trade-offs.
Right. What we observed is that when you develop, without staleness, when you develop the model, we spend a lot of time tuning the model parameters, all that. Eventually we get something that's good, that's comparable to human classification. But once we start doing staleness even a little bit, it goes so off. It converges fine, but it converges something very different, and its quality is quite unpredictable.
Oh, okay.
Yeah, I think we should take the rest of
Thank
this
you.
offline. Very good discussion,
Yes.
though.
Okay.